Good morning, good afternoon, and good evening to all of you who have joined this webinar today. As you might be aware, we're organizing this webinar under the OrbitalAI Challenge, organized by ESA's PLab. The OrbitalAI Challenge is specifically aiming to develop prototypes, AI for you algorithms that will be running on board either VSAT-2 using multispectral Earth observation data, or on the ISS using hyperspectral data in cooperation with Microsoft and Thales Alenia. And today, what we want to do is to introduce you to some AI for Earth observation concepts, inspire you to think of ideas, to develop your prototypes for the OrbitalAI Challenge, and to further improve so that you have a chance to shoot up your prototype into space. And then we are going to move on to the next presentation. We have also two speakers from Microsoft here with us today who are organizing part of the challenge, of the OrbitalAI Challenge. First up, we have Roberto Estevao from Microsoft Research Brazil. He's a software engineer working on AI for Earth observation with a focus on sustainability. And he has been developing applications using open source AI algorithms and Copernicus Sentinel data. So Roberto, the floor is yours.
Hello, everyone. I'm Roberto Estevão. I'm a research software engineer at Microsoft Research. And today I'm going to talk mostly about SpaceEye, which is a technique for generating cloud-free imagery that's available on FarmVibes AI. So FarmVibes AI is a platform for ingesting and processing geospatial data with a focus on agriculture and sustainability that the team released a few months ago. And in FarmVibes, users can run customizable workflows that combine data ingestion and processing. And some examples that are available on our GitHub page include segmenting cropland regions given a time series of satellite data, estimating land degradation with NDVI trends, weed detection on farm fields using drone imagery, and SpaceEye, which is the topic that we'll cover in more detail in this presentation. If you're interested in learning more about FarmVibes, you can do so on our GitHub page, available on github.com/Microsoft/FarmVibes-AI, and link in this slide. We have implemented workflows for ingesting a variety of data in FarmVibes. For satellite imagery, we support sources such as Sentinel, Landsat, MODIS, NAPE, and Airbus. We also support several types of auxiliary data that can be used as targets or additional inputs to your model, such as cropland data layer, digital elevation maps, soil information, canopy height measurements, and we also support weather information such as precipitation and weather forecasts. We have a full list of available workflows on our documentation in our GitHub repo that is also linked in this slide. But in this talk, we'll focus more specifically on SpaceEye, which is a machine learning model that operates on Sentinel-2 imagery. The Sentinel-2 mission is composed of 2 satellites that carry optical multispectral instruments, and these instruments sample 13 bands in relatively high resolution. There are 4 bands at 10-meter resolution, 6 bands at 12-meter resolution, and 3 bands at 60-meter resolution. For the Sentinel-2 L2A products, which is what we're using, we have 12 of the 13 bands available. And more specifically, for this presentation, we'll focus on the 10 bands that are available at 10 and 20-meter resolution. The revisit time of Sentinel-2 is around 5 days, which makes this a very useful source of monitoring of image for monitoring changes in the ground. In the context of agriculture, for example, the bands available can be used to compute several vegetation indices that are very useful for monitoring crops. And in this slide, just as an example, I'm showing the RGB representation of a region, as well as the normalized difference vegetation index, or NDVI, which is a very popular index for estimating things like crop growth or crop health. And we can see that the index is high in regions that are, that have a lot of vegetation, that are very green, and low otherwise. Since Sentinel-2 satellites use optical instruments, clouds will obstruct the view to the ground. In fact, a large portion of the captured imagery is covered by clouds, something between 50 to 80%, depending on the type of clouds and the region. And since the reflectance of the clouds is very different from what you want to see in the ground, it is very important to detect and avoid cloudy regions when handling imagery. For example, if one is tracking a vegetation index in a crop field over time, you should avoid the cloudy samples since those will have very different values, even if nothing changed in the crop field itself. So given this context, let's talk about SpaceEye. So SpaceEye is a neural network-based technique for clouding painting. And the idea is that we generate cloud-free multispectral imagery by fusing information from Sentinel-1 and Sentinel-2. So Sentinel-2, as we said before, uses a multispectral optical instrument, and that's what we'll try to reconstruct using SpaceEye. And Sentinel-1 satellites carry a synthetic aperture radar, or SAR instrument, which is largely unaffected by weather conditions. So the output of this model is a raster that contains 10 of the 12 Sentinel-2 bands at 10-meter resolution. And the model generates missing data by interpolation via temporal and spatial attention, which means it is able to look for similar patches in a spatial temporal window. Due to its temporal component, it is also able to generate predictions even if no imagery is available that day, or if the image that is available is completely covered by clouds. So in FarmVibes.ai, the whole process for generating cloud-free images can be done by running the SpaceEye workflow. The workflow takes a region of interest and a time range as input and performs all the necessary data acquisition, pre-processing, and model inference in order to generate daily cloud-free imagery. I'm just going to describe all the pre-processing of the data so you have a better idea of what it takes to run this model. And this workflow can be divided into three main parts: Sentinel-2 pre-processing, Sentinel-1 pre-processing, and SpaceEye inference. So the Sentinel-2 pre-processing workflow can be divided into roughly 5 steps. We first list all the products, the Sentinel-2 products that intersect with the input region and are inside the input time range. We then filter those products and keep a subset that is necessary to cover the input region. We download the data for each of the selected products, and we pre-process them by resampling all bands to 10-meter resolution and generating cloud masks from the cloud geometries. Finally, we improve the product cloud mask by running machine learning models to segment clouds and cloud shadows, and we merge all three masks into a single usable or not usable mask. The Sentinel-1 pre-processing workflow performs similar list and download operations to download Sentinel-1 data that intersects the selected Sentinel-2 products. And this data is then preprocessed by standard SAR preprocessing steps like the rain correction, and it is also resampled to match the Sentinel-2 tiling grid. Finally, we merge all the products that intersect with the same Sentinel-2 tile. So the output is Sentinel-1 data that is spatially aligned with Sentinel-2 imagery, also at 10-meter resolution. On the SpaceEye inference workflow, we split the input data, which is Sentinel-2 imagery, cloud mask, and Sentinel-1 data, into spatial temporal chunks. We perform inference in the model for each chunk, and we merge all the results in the end. This enables the user to specify time ranges or regions of interest that are larger than the model's inference window. I'll now briefly describe the main components of SpaceEye. So at first, both Sentinel-1 and Sentinel-2 are mapped from pixels to features via their respective encoders. So these encoders are applied to each image in the sequence separately, and they subsample the data spatially by a factor of 8. The core of the SpaceEye architecture is a multimodal mask attention module. And the idea is that the Sentinel-1 features are used as queries and keys to guide the attention mechanism, while Sentinel-2 features are used as values. The attention weights are masked according to the cloud mask in order to restrict the model to only attending to cloud-free regions. So this allows the model to in-paint cloudy regions by mixing information from similar cloud-free patches in our spatial temporal window. The output of the attention module is then mapped back into pixel space via the decoder that is also applied independently for each image. We can train SpaceEye in a supervised fashion by feeding it cloudy images and using cloud-free imagery as ground truth, because you don't know what the actual values would be if the image wasn't cloudy. So instead, we trained it in a self-supervised fashion. The idea is that we generate synthetic cloud masks that are added to the real cloud masks, and the model is then trained to reconstruct pixels under the synthetic masks. Since those pixels are not really cloudy, we can use them as ground truth values in a loss function that can be optimized using gradient descent. If you're interested in learning more details about the architecture or the training procedure or evaluation for SpaceEye, please read the paper authored by Mingming Zhao, Peter Olson, and Ranveer Chandra that I'm linking here in the slide. I'm just going to show a short video that exemplifies the application of SpaceEye in monitoring crop fields. SpaceEye is not really restricted to agriculture-related applications, but since our group is focused on that, that's what I have most of the examples for. So at first, we can see RGB reconstructions of the data, and we can see that Sentinel-2 imagery is not available every day, and several regions of the images are covered by clouds. SpaceEye is able to generate images that are cloud-free, and we can generate these images for every day. Besides the RGB reconstructions, we can use the other multispectral bands to reconstruct indices that are useful in crop monitoring, such as NDVI, which we're showing the video now. And DWI as well, for example, which we're showing in the video now. Like Sentinel-2 imagery, SpaceEye generated bands can also be used as inputs to other models. So we have a crop segmentation example that trains a convolutional neural network to segment crop fields, given a stack of NDVI rasters that can be computed, for example, on top of SpaceEye. The idea is that crops grow at different times throughout the year. So looking at how the vegetation index progresses can be useful in classifying regions that belong to crop fields. So we use the USDA cropland data layer, or CTL, as ground truth to train the model. For this example, we combine our crop indices to create a binary crop mask, which will serve as ground truth. And we can then run SpaceEye for a certain time range, compute NDVI rasters over time, and then stack them in the channel dimension and feed it to a fairly standard convolutional neural network based segmentation network that is then trained to output a cropland segmentation map like this one. Just as a quick example, here is what the output looks like on the validation region on the top and the reference mask in the bottom that was obtained from CTL. So yeah, that's all that I wanted to show for today. Thank you for your time. If you're interested in learning more about SpaceEye or the other applications, you can check out the Farm Vibes repo on GitHub.
Thank you very much, Roberto. Just one quick question. You're using SpaceEye to fill gaps for clouds, but do you also generate imagery for days in which there is no Sentinel-1 or Sentinel-2 product available?
Yes. So SpaceEye would generate images even if there is no data available for that specific day, as long as there is data on the spatial temporal window around it, right? So either preceding that date or afterwards. So it's going to look for data both in spatially for on the same date, but it also looks for that same region through time. So it is able to looking forward and backward in time estimate what that region would look like on that day.
And how big can that window then be?
Yeah, so this is a tunable parameter, I guess. The larger the window, the more compute we use. The experiments are usually, for spatially speaking, we use 448 by 448 patches at 10 meter resolution, so 4.5 kilometers, I guess. And in terms of days, we usually use a 48-day window. And if we want to predict further, we can split those into chunks and then do predictions for each chunk and merge them again.
Okay, good, thank you. We have a few other questions in the chat, but they're more related to the challenge in general, and we'll take those right after the last presentation from Kevin. And meanwhile, Roberto, many thanks for your presentation. And so our next presentation is from Kevin Shea. He also works at Microsoft on Microsoft research in the US. He's a researcher in AI working on algorithms that can be trained directly in space. And he will be showing some of the publicly available results of his field of research. Kevin, the floor is yours.
Thanks for the introduction. Can you guys hear me?
Yes.
Okay, good. Yeah, so the next presentation I'm going to talk about is the recent work that we did, that we tried to do AI training in space, which means that we use the compute resources on satellites to do AI training. And this is a joint work with my colleagues at Microsoft, as well as my intern at USC. So, so there's actually a lot of these AI-driven space applications, and many of them actually require up-to-date AI models to do really good job. For example, disaster navigation. They usually this data set, the data that comes with the disaster comes in real time. They also happen very rare, so it is hard to pre-train those models. In some other situations like weather forecasting or environmental monitoring, it is also beneficial to train those models up to date, continuously train to get really good results. However, there's this recent trend in satellite launching that from really large satellites to today, these nano satellites or CubeSat, which makes it very, very cheap to launch those satellites. And as a result, there's a huge growth in terms of the number of satellites that's going to launch. And all these satellites are going to collect a lot of data sets. And the major challenge today to enable this AI training becomes, how do we download all these data sets to the ground to train the model, which is the traditional approach that we do this. However, what we realize is that when you launch so many satellites, the fundamental bottleneck becomes ground stations, because the ground stations turns out to be very expensive to deploy, and also there's a lot of regularization issues because they transmit signals, and you have to go through in different areas. There's different regularization issues, so it takes a lot of time to deploy a lot of ground stations, and as a result, there are actually a lot of data that's going to be collected, but many of them cannot be downloaded to the ground. So the alternative approach that we propose is that we can actually leverage federated learning to exchange AI models instead of downloading the data, or at least not download all the data to the ground. So here, applying the federated learning concept, satellites behave like the clients. So they train the model with the data they collected, and then they exchange their trained model with ground stations. and the ground stations will aggregate those models and then send the aggregated models back to other satellites. However, if we just apply the existing federated learning solutions to this problem, there is a lot of issues. So the most obvious thing to do is using synchronous federated learning, which is the vast majority solution in federated learning space, where the idea is to get all the updates from all the satellites or all the clients, and then send the updated model to everyone, and then to continue. For example, in this particular case, there's one ground station and 3 satellites, and they're going through time. So we can see that when there's a circle, that means that there's a contact between satellites and ground stations. And so if there is, as you can see, the satellite 1 and 2, they have contact with ground stations, but satellite 3 doesn't have one. And so during this time, they are all waiting for a contact from the last satellite, and they're not doing anything until there's a contact from satellite 3, and then we can do another update, and then send the update to all the satellites only after they come into contact with ground stations as well. So all this time, there's going to be a lot of idle, and that will slow down the machine learning training. And so the other approach is asynchronous federated learning, which essentially is keep updating the global model whenever we receive an update from the satellites. But the issue with this approach is that when those low connectivity satellites come in, the model they train based on is already very old, which is the stale. And this stale model contribute these stale updates can actually create a lot of issues with the global models and can even diverge the training. And to solve this problem, we propose a solution we call FedSpace. And the key idea here is that all these time-varying topology of satellites and ground stations is actually somewhat deterministic, and we can actually predict and pre-compute them. And so as a result, what we are actually trying to solve really is an optimization problem, where the goal is that because we know the staleness distribution, given a aggregation schedule, meaning that we know which time we are going to aggregate these models, then we can pre-compute those staleness distribution. And given distribution and training status, we can actually predict what is the quality improvement of the model. And so the goal really is to find that aggregation schedule so that we can maximize the model quality. And to solve this problem, the FedSpace algorithm take 2 steps. The first step is to train the utility regressor, which by feeding it into with different staleness distribution and training status, so that we can come up with a predictor, so that we can predict this utility function, or which means the model quality improvement. And then we use that regressor to find the aggregation schedule at runtime based on the real-time training status and the distribution of the network, to essentially using random search to search different potential aggregation schedules, and then to find the best one that would potentially maximize the training progress. And we evaluate this algorithm with a diverse set of data set and different settings. So in this particular setup, what we did is we used the functional map of the world data set, and also with PlanetNet satellite networks using 12 ground stations and about 191 satellites to train the model. And as you can see the results here, we also compare against all these other existing federated learning solutions, and also a more recent solution called FedBuff from Facebook. And we can see that FedSpace outperform all of them significantly and can reduce the training time by almost 40%. So a quick summary is that federated learning provides a potential solution so that we can enable AI training in space, but we cannot apply federated learning as is to this setting because it creates idleness and stillness challenges. So to solve this problem, we propose an algorithm that essentially take advantage of the deterministic and non-network topology, and then we predict how we can aggregate those models effectively to trade off between these idleness and stillness problems. And in the future, we're also going to work on other constraints such as limited compute, limited energy, and limited bandwidth to come up with an even more practical and complete solution. Thank you.
Thank you very much, Kevin, for this presentation. At the moment, so we still have about 13 minutes left in this webinar. So the floor is open for questions. If you have any questions, please put them in the Q&A so we can get to it. We also received some questions in the meanwhile that are related to the challenge itself. For example, one person asked what the level of processing needs to be assumed for the data to be used in the challenge. And so what excuse me, if you register to the challenge, either the FESAT2 challenge or the imagery challenge, you will find in the data tab on the website a notebook that will allow you to generate the data, but also a pre-processed data set that you can start to use. So all of these data are already available for you on the platform. For those that are more familiar with Earth observation data, as Nicolas answered during the webinar, you can, for imagery, it goes up to level 1C, reflectance top of atmosphere, while for FESAT2, it's a range from level 1A, radiance, coarse registration, coarse band-to-band registration, to level 1B, and finally level 1C, top of atmosphere reflectances with fine band-to-band alignment and georeferencing. But there is the pre-processed data set as well that you can use. If you need to think a little bit about questions in the meanwhile, I also have some more information for you. So today we had this bit of an inspiration on which prototypes you can develop, how you can further, what's the leading technologies or the leading algorithms in this field that you can be inspired by. And in the meanwhile, you still have 2 months to work on your prototype before it needs to be submitted. But we will be helping you out in the meanwhile as well. So for instance, so this webinar will be followed by a next webinar where we'll go more in depth about how to optimize your AI model for onboard processing. Because it's one thing to create an AI model for using Earth observation data. It's another thing to be able to run that on a chip on board a satellite that's 700 kilometers away. So that webinar will focus on ways to optimize it, reducing the size of it, reducing the computing capacity that it requires. So join us on the 23rd of May for this webinar. Then by the end of May, we will ask you to submit your prototype's initial model to get an idea of where you're going, if you to also make sure that you are already thinking of how am I working this out. And in the meanwhile, because you're really coding right now in this challenge, we will be organizing some drop-in sessions. So get ready to ask our experts any questions that you might have, any things that you might be stuck with. In the next week, you will receive an email from us announcing the time and date for a drop-in session. And of course, as always, if there's any questions that you have, you can always reach us on hello@ai4eo.eu or on the forum on the AI4eo platform. I see that in the meanwhile, you have been asking some questions. One question came, so when the solution is deployed, will the pre-processing be done, or should we account for that in our workflow? Nicola, can you?
I can answer for this one, at least for the FISA2 track. All the pre-processing, the tiling and so on will be done separately. So you don't have to account for that in your workflow. It will be done natively, and you will just have to apply your model on patches, like on 256 pixel patches, and that's it. No need for you to consider this aspect. It will be done before.
Thank you. Secondly, the question was what needs to be submitted as part of milestone 3. So as part of milestone 3, we will expect that you have an initial model coded in the Jupyter notebook that's been made available, and that you submit that Jupyter notebook so that we can start to have a look at it. So that there's no need, I believe, at this time to have the model architecture included. And also for the final submission, at the final submission, you will also be submitting your Jupyter notebook. The IP, it's written on the website, but Jonut, maybe you have that answer ready for us on who would own the IP for the models?
The idea is that the IP remain to the challenger.
Yes.
So as organizer, we don't own the IP. Then there will be one-to-one discussion, especially for the one that will be granted and for which will fly the model. One of the requirements is that all the data generated by the AI model on board, especially for the FISA2, all this data will be open sourcely and distributed openly to the community. So at least for the FISA2, there will be no, let's say, no commercial, let's say, data aspect, and all the data will be disseminated openly and free, available to the community. And of course, we don't disseminate any of your ID to the rest of the community. All the things that you submit is kept internally to ESA and all the partners in charge of the challenge, of course.
Okay, thank you. There is also one question related to security, but this is something that we are taking offline. In the meanwhile, would there be any other questions? Open. There are some questions about the AutoIce challenge. The person that has asked that, can you please email us at hello@ai4eo.eu so that we can answer you there, and then we can take it offline. But if there's no further questions about the OrbitalAI challenge or any of the presentations today, then I would like to thank Pierre-Philippe, Roberto, and Kevin again for their presentations. Nicolas also for answering our questions. And in the meanwhile, then I wish you lots of luck with the OrbitalAI challenge, and I hope to see many of you submitting your next milestone and your prototype towards the end. Thank you very much. Have a nice evening.